Hi guys, so you should have made it through all your Pogles and your bookwork so far and had a really good introduction to chemical reactions, how to balance them, how to identify what types of reactions are occurring, and then also about double replacement reactions that form precipitates. Okay, I'm going to do a little bit of a review and debrief with you on that, but I just wanted to say hi and hope you're all doing well. You really are killing it on this offsite learning. I'm just so proud of you, so please don't hesitate to reach out. Keep it coming with those questions, and we're going to make it through this. So I'm going to go ahead and close the webcam, but I just wanted to say hi. So we'll close this up and get started with our debrief. So, if we were to look at some of the summarizing discussion questions that you would have had we been in class, this is an example of a question that we would have had. So, just to do a little bit of a review of the different types of reactions that we may see and be working with, I just wanted to go over that with you first. So, first of all, we have synthesis reactions. And in very basic terms, it's basically taking two smaller atoms or molecules or compounds and combining it into one larger one. Okay. And so if we had two separate atoms like sodium and chlorine gas and converted it into sodium chloride, you would end up with a synthesis reaction. And so if we look at that example, sodium plus chlorine gas, because remember, chlorine is one of those 7 diatomic molecules that can never exist alone in nature that Mr. George had you memorize, and that forms sodium chloride. Now, the one thing that we now know too is that in order to honor the law of conservation of mass, we need to balance these equations. And so when we're writing these equations, it's fine to use subscripts like the 2 on chlorine to show that that is a bonded molecule. But whenever we're balancing, we can only use coefficients. And so in order to balance this, I would look at all of these elements and say what's out of balance and make sure that it is balanced using coefficients. And so I look at my sodiums. I have one on the left side of the arrow. I have one on the right side of the arrow. So I'm balanced there. But for chlorine, I have 2 on the left side and 1 on the right side. So I have to throw a 2 in front of here to make the chlorines balance. But now the sodiums are out of balance, which is not a big deal because I can just throw a 2 in front of there. And now we're perfectly balanced and honoring the law of conservation of mass. So it's really important, especially as we go into stoichiometry for our next lessons in the next 2 weeks, that you are working on balancing your equations. I've given you lots of different resources to access to make sure that you're feeling good about that. Okay. So the next one that the next type of reaction that we learned about is decomposition. And decomposition is exactly the opposite of synthesis. So it's taking a larger molecular compound and then it breaks down in the reaction into two smaller um, elements or compounds. Okay. And so, exactly the opposite of this, we could take salt and break it down into sodium and chloride. We can take water and break it down into the separate gases. And remember, same with chlorine, H and O are part of those diatomic molecules that can never exist alone in nature. And so we have to write them like that. And again, if we were to balance these, we see that there's 2 H's on the left, 2 H's on the right, but only one O on the left and 2 O's on the right. So if we throw a 2 in front of here, we balance the oxygens, but we now have 4 hydrogens, so we have to balance hydrogens by doing it like that. Okay. And it's multiplication with the coefficients. It's like distribution, not addition. Okay. So hopefully that makes sense. So I'm going to erase this stuff. The next type of reaction that we are going to discuss is a single replacement reaction. And so single replacement is where I always say this is kind of like the cheater reaction because you have a compound and a single element. And then after the reaction occurs, the single element comes in and replaces one of the things in the compound. Okay. And so an example of this might be potassium chloride plus sodium would yield sodium chloride plus potassium. Now, the only way that you know how this is going, like which one's going to replace which, is for ionic compounds. So single replacement will always just be about ionic compounds. And so since ionic is always between a metal and a non-metal, I could never have sodium and potassium go together because that would be a metallic bond, where it'd be two metals coming together. And so since I know that this has to be ionic, I know that since sodium is a metal and potassium is metal, those are the two that have to swap places. So that's one thing to consider when you're thinking about single replacement and the next one, which is double replacement, because those can only be used for ionic compounds or sometimes with weird gases. Another example would be like if the single element might be a gas, it could then take the place of the other non-metal. But again, you would only have the compound itself being ionic. So keep that in mind, okay? So the next one is double replacement. And this is like the do-si-do partners that swap places. So we have two larger compounds, typically within aqueous solutions, so that during the um, reaction where this arrow is occurring, there is actually some like swaps of partners that are happening. And so then you would end up with AD plus CB as the reaction. So a good example of this would be something like sodium nitrate plus silver uh, iodide yields silver nitrate and sodium iodide. Again, you know which has to go with which because it's all ionic. And so you could never have silver and sodium go together because they're both metals. And so you need a metal with a non-metal so that you can only swap the partners that are needed for that. Okay. So that is my little lesson on. Oh, there's one more that we need to actually talk about that doesn't get talked about as often, but it's combustion. And combustion's really actually quite easy because it's basically just any any carbon-based molecule. So combustion, any carbon-based molecule. So maybe C3H8 plus oxygen gas. Okay, because fire always needs oxygen to burn. And so that has to be part of one of the reactants. Will always, 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 always produce carbon dioxide and water. Okay. And then you can balance those from there in order to get to honor the law of conservation of matter. This is actually a good one to balance. We should do this. I thought of this off the top of my head, so it might take me a minute, but let's balance this. So I always like to leave things like water till the very end because it's kind of a like I don't know, it's the wild card that just seems to click into place at the end. So I'm going to focus on my carbons first. And so I have 3 carbons on the left, I have 1 on the right. So I'm going to throw 3 in front of that in order to make it 3 carbons on both sides. Then I have my oxygens now at 6 plus 1 is 7. But if I balance my hydrogens, I can throw a 4 in front of here to get that to be 8. And so now I have my water as 8 hydrogens and then I have 8 on the left, but my water or my oxygens are now at 6 between those two and plus 4 with those because of this plus sign in the middle there. And so I have 10 total oxygens. So I just need to throw a 5 in front of there and I have a perfectly balanced chemical equation. So hopefully that's starting to kind of click and make sense for you. If it's not, review the Khan Academy video. There's also a lot of like tutorials and helpful web worksheets on the internet, so you could totally check that out. But let me know if you have more questions. I can totally go through things with you. I'm happy to. So that brings us to the end of the types of reactions. The next one I want to talk to you about is solubility. Okay, and so if I go to our next set of summarizing discussions here, we have predicting products is something that's a pretty important um, t- um skill that you'll need to know how to do as you proceed in chemistry. And so there are a lot of different ways that you can predict products, and it's ultimately first you need to know what type of reaction you're dealing with. And so we're going to first focus on just the double replacement because that's going to be the ones that we're going to have to identify the solubility rules with. And so if we look at E here on the screen, aluminum sulfate plus calcium hydroxide, I'm going to write that out. So aluminum sulfate. So aluminum, of course, is Al with a 3 plus charge. Sulfate is a polyatomic ion because it has an 8 ending. So it's SO4 with a 2 minus charge. And so I know that since it has a 3 plus and a 2 minus, and it's a metal and a non-metal, it's going to be an ionic bond. And so I just crisscross these charges to write the ratio at which they need to be together. And so it would be Al2 SO4 3 would be the actual reactant of how we would write this. And then we're adding it to calcium hydroxide. And so it's hydroxide. And so even though it has an ide ending, it's not hydride. It's not just plain hydrogen. It's hydroxide. And so we know that that's also a polyatomic ion. And so I have calcium, which is my 2 plus charge, and hydroxide, which is OH1 minus. And so again, I'm going to crisscross these charges to get the ratios at which they need to be. It's going to be Ca and then OH in parentheses because we can't change the subscripts with a 2 on the outside. Now, both of these are going to be aqueous, which means that they're both soluble in water. And I can tell that based off of the solubility chart that's either in the POGL or if you go to page 372, I believe it was, in your textbook, there is table 11.3 that are the solubility rules. And if we look at this, it says that for sulfate salts, they're all soluble unless they're combined with certain ones, but none of those are aluminum. And hydroxides are all soluble as well. Unless they're, or I'm sorry, are insoluble, which means they would be a solid, unless they're combined with a alkali metal. And so calcium hydroxide is actually going to be aqueous because of calcium being an alkali metal. And so we then perform the double replacement reaction with these two. And so we have the metal of aluminum going with the non-metal of hydroxide because those are the only two swaps we can make based off the ionic bonding. And then we're going to have calcium go with sulfate, okay? So it's important to keep the charges the same. Like you can never change the charges, and so we have to change the ratios at which they bond. And so aluminum, again, has this 3 plus charge and hydroxide has a 1 minus. So if we crisscross those, we end up with Al OH3 plus, and then we have our calcium with a 2 plus charge, sulfate with a 2 minus. When they crisscross, they're both 2s, so they crisscross and cancel. And so we end up with CaSO4 because that's the ratio that they need to be into. And then we need to check their solubility. And so we just looked up at the solubility rules, and it said the hydroxide is insoluble unless it's combined with an alkali metal. Well, guess what? Aluminum is not an alkali metal. And so this is going to end up being insoluble, but it'll form a solid. And that's why we write an S for that to represent the state of matter, not solubility. So it's S for solid. Aqueous means that it dissolves in water. It is soluble. And so sulfates are also still going to remain soluble. So this is going to be our aqueous solution. And so then we have our final equation. And if we balance this, then we need to be able to throw a 2 in front of here to balance our aluminums. And then we need to throw a 3 in front of here to balance our sulfurs. And then we need to throw a 3 in front of there to balance our calciums. And it looks like we are totally balanced then because our sulfates are balanced, our calciums are balanced, our hydroxide are balanced, and our aluminums are balanced. So this will be a really interesting test for you to work through. This is one of the coolest labs that we usually do is to do double replacement reactions because what we would actually see if you were performing this actual experiment is that you would combine two liquids together, and then this solid right here would actually form instantaneously into a solid within a liquid, and it's so cool. And so you're going to see some videos of this. You're also going to get to do a virtual lab. I just wish you could see it in person. It's really neat. So don't hesitate to look up precipitation reactions too, just to see what those look like. And then there's going to be a really cool video actually in your quiz that you'll have to watch and analyze, but the video itself is really neat. So I hope you enjoy it. Please let me know if you have questions. Use those resources. I don't care if you use your books and resources on the assessments because I know how challenging this is. So just don't use each other if we can avoid that. But so no calling friends and whatnot, but use those resources. All right, you guys, I miss you. I'll talk to you on our next debrief. All right, bye.